Hi, thanks for coming and thank you for the lucky talk. I'll continue my talk from yesterday. So we're trying to show an exponential separation of information and communication, and this was our main result. We show separation between communication and information, and basically for every parameter k, we'll see a function and a distribution such that the information cost of the function is very low, it's only O of k, but the communication is at least exponential, it's at least 2 to the k. And this will mean that interactive protocols cannot always be compressed to their information content. So what I want to do in this talk, I want to tell you a little bit more about the separation, about the example that separate information and communication. So yesterday I sketched a search problem and a simplified distribution. Today I want to show you the actual construction, the actual function, so it will be a proper Boolean function. And the actual distribution, it's slightly more complicated than what we had before. And I want to show you the upper bound that I didn't get to show you yesterday. So we'll see some more details today, basically, and hopefully get a flavor of this result. Okay. So the first few slides are going to be very close to what we had yesterday with one difference. So let me just remind you what we're doing or how we construct this example. We're going to have an underlying tree. It's a complete binary tree. We're grouping every 100k layers together and call it a multi-layer. And this tree is very, very deep. It has 2 to the 4 to the k multi-layers. And we had input, so Alice got some x and Bob got some y, such that x contains 1 bit for every vertex in the tree, and y contains a possibly different bit for every vertex in the tree. So this is a vertex. Alice gets some bit, Bob gets another bit. And we remarked that the input size is huge here. Let me remind you the definition of typical vertices. So we assume that Alice owns the odd layers and Bob owns the even layers. And then the player who owns a vertex really tells us what is the right way to go if you reach this vertex. So if Alice owns the vertex and her bit is 0, it means that the player is supposed to go left. And if she has a 1, they're supposed to go right. And then the important definition was of a typical node, where we said that a node is typical, so you need to fix I, x, and y with respect to the multi-layer and to inputs. So it's typical if it's in a multi-layer that is after multi-layer I. So let's take this guy, suppose that it's just after multi-layer I, but it can be anywhere in here. And that the subpath leading to it in multilayer I has at least 80% correct children. So we only look at this part of the path and we check that 80% of the time we went to the right direction with respect to x and y. So x and y tell us what is the right direction. And I'm asking you to go at least 80% of the time to the right direction with respect to the inputs. So this was the definition, and we also remarked that typical vertices are arranged in subtrees. So if this guy is typical, every node in its subtree is also typical, and those are the typical leaves. So this we had from yesterday. Yesterday I defined a simplified distribution mu. I want to give you the proper distribution that we're using in the paper. So as we said before, we have 2 types of vertices. The first type is called non-noisy, and it means that x and y are choosing at random and are choosing to be the same. So for non-noisy vertices, we give Alice and Bob the same bit. It's just a random bit, but it's the same bit. And for noisy vertices, x and y are the bits given to Alice or Bob are selected independently at random. Okay, so no noise means that they have the same bits. Noise means that the bits are independent. They have no idea what the other guy got. And this is the actual distribution. It's kind of similar to what we had before with a twist. Okay, so as we've done yesterday, you randomly select a multi-layer. Suppose you selected this multilayer. And then all the vertices before multilayer I, all the guys in here, are set to be non-noisy. Okay, so Alice and Bob will get the same bits for every vertex in here. Multilayer I is noisy, so every vertex in multilayer I is set to be noisy. All the guys in here, all the vertices in here are selected, the bits for them are selected independently for Alice and Bob. And now this is the twist, this is the new thing. For layers after multilayer I, we'll have what we call bursting noise. It looks like that. Okay, so before what we had yesterday is everything in here was white, it was non-noisy. Now we'll have some of the vertices will be noisy and some of the vertices will be non-noisy. And actually the non-typical vertices will be noisy. So if this guy is not typical, so this part of the path does not contain 80% correct children, this guy is not typical, all the subtree rooted at this vertex is going to be noisy. But if this guy is typical, then everything beneath it, its subtree is going to be non-noisy. So this is a slightly more complicated definition. The complication is only here. So this was non-noisy, it's still non-noisy. This is noisy as it was before. And before I defined this to be non-noisy, now part of it is noisy and part is non-noisy. And we think that you can work with everything in here being non-noisy, but we don't know how to show that. And it's very crucial for the actual analysis to have noise even on the bottom. And I'll say a little bit more about that, but this is also the reason we call it the bursting noise, because like if this vertex is noisy, the noise kind of bursts out of it. This is the reason for the name. Again, we don't know if it's just technical or it's really needed. We think it's technical, but it's really, the proof really relies on this kind of noise. But this is the definition. So there is one special layer, this layer, which is noisy. Everything before is non-noisy, and on the bottom we have this weird tapestry with noisy and non-noisy, which we carefully select, and I'll remark about that later. Questions about the new actual distribution? Okay. So yesterday I told you that the goal of the players, this was the search problem, right? The goal was to find and output the same typical leaf. So give me anything in here, like any typical leaf is okay, as long as you give me the same typical leaf. So again, we're just asking you to find some leaf such that this part of the path leading to it contains 80% correct children. And this was a search problem because there are many possible outputs for every pair of inputs. So I want to convert it to a function, but before, let me just repeat why we think you should maybe believe me that the communication should be high. So I argued that guessing a random leaf is not a good idea because there is a very small probability of it being actually typical, because a random leaf will have 50% of the path correct, and we ask for 80%. And we also said that the key to solving is knowing multilayer I. If the players know multilayer I, they can just follow the path from, say, this point, because they know multilayer I, and they can just communicate the information on multilayer I. The thing is, the tree is so deep that they can't find multilayer I efficiently, so they somehow need to give information on all the multilayers, and this is very wasteful. So of course the analysis is not that simple, and maybe now I should say that Anoop and Makrand have a simplified proof of this lower bound, and they're going to present it tomorrow at 5 p.m. if you want to listen. So definitely what they do is shorter than what we do and is simplified, so I think it's worth the effort. Okay, so I won't talk about it. I guess they'll give the details for that. But this is kind of a sanity check. And you can see that those claims, they hold even without the bursting noise. I mean, I told you about that yesterday. Why do I put this bursting noise in? Why do I need, like, maybe it's enough for this multilayer to be noisy? And the reason is kind of on an intuitive level, the bursting noise makes the game harder for the players. They have less in common. If everything in here is non-noisy, it's all white, then they have more in common. Maybe they can somehow use that to solve the game. By adding noise here, I make the game harder for them, and therefore potentially easier for me to show lower bounds on the game. So really the bursting noise is only used in the lower bound proof, and this will be, so this kind of noise also exists in Macrand and Anoop's proof. So we don't know how to get rid of it, but it helps us for the lower bound. Good. So now I want to convert to a function. So remember what the task that before the search problem was just give me any typical leaf. But now I want a proper search, I want a proper Boolean function. Okay, so the output size here was huge and it was a search problem. Now we want a function with small output size. Okay, so here is how we do that. What you do is you update your distribution mu. Okay, so this was the distribution mu. This is the way we selected x and y. Now we do something slightly different. We first select x and y as before. Okay, so suppose we selected things according to the scheme. Now we do an additional step. You randomly select some bit b, either 0 or 1 with probability half and half. And then for every leaf, you add to yv, to Bob's input, you add b to it. Okay, over gf2, okay, mod 2. Okay, so again, you construct x and y as before, but now you have this special bit b. What you do is you give x to Alice, exactly as before, but before giving y to b, you add this b to every vb. So this leaf will get, it used to have some value, right? Now we add b to it, and we do that for every leaf, but just for Bob. Okay, so this is the construction. You add b to yv for every leaf v. And the function is, if we give the players x and y, we expect them to give us b back. And this is a well-defined function. Okay, so it's a function, great, it's a Boolean function, clearly. Why would it make any sense? So, okay, first note that for any typical leaf, when you sum up vb and yv, xv and yv, you get exactly b. Why is that? Because if the leaf is typical, right, it's somewhere in here, it's non-noisy. See, the white is non-noisy. X was equal to y to begin with. So to begin with, x was equal to y, and then we added b to v. So to y. We added b to y. So now the sum is b. Okay, so before they were equal, and now we added this b to y, so the sum is b. So this says that if you want to determine b, it suffices to find a typical leaf. If you solve the search problem, then you can easily solve the function. Right? Because if I find a typical leaf, I just sum the bits and I output this b. It's very easy. Okay, but note that if you have a non-typical leaf, then the sum is going to be just random. Because for non-typical leaves, right, those are non-typical leaves, you can see that they're noisy, which means that x and y to begin with were just independent. And then we added some b to y. They're still just independent, right? So the sum is going to be random. So if you know a typical leaf, then you can solve. And if you try to use a different leaf that is not typical, then it wouldn't give you anything. Okay, so of course it doesn't mean that if you solve the function, you solve the game. It just means that, just one direction here is true. If you solve the search problem, you solve the function. But we don't know that the other way also works. So this is the construction, and this gives a function. And maybe like on some intuitive level, so I can't actually see the clock from here. 15. Okay, great. So let me maybe say it again how we were doing this function thing. Okay, so we have all, like take this set to be the set of all leaves. Those are all the possible outputs. And there is, for every x and y, there is a set of outputs that is correct. Those are the typical leaves. Okay, so for every x and y, we have the typical leaves, and this is the set of all leaves. And what we do is we want to map the typical leaves to some b, some bit b, and we want to map all the other leaves to random or arbitrary bit. And this is exactly what we do. So for typical leaves, we make them share b. Okay, so x and y are shares of this b. If you XOR them together, you get b. And for all the other leaves, if you XOR together, you get nothing. It's just random. So this is kind of a more general statement, right? You can always take the good set, the correct set, and map it to some bit, which is the output of your Boolean function. And all the rest, you should make sure that they give no information about the actual b. And this is basically what we do. And this is a proper Boolean function. Questions about the function? Okay, great. Okay, so now I want to show you the protocol with low information cost. So hopefully you have some vague idea of why you should expect that the communication is at least 2 to the k, but now I want to claim that the information is at most, is exactly O of k. And this direction is much easier than the lower bound. It's an upper bound. We'll see the protocol. It's not complicated. The analysis is not very simple, but it's much simpler than the lower bound proof. Okay, so this is the protocol. There is a minor bug that we'll fix, but it basically goes like that. You start from the root, and then on every vertex v you encounter, the player who owns v sends his bit with probability 90% and send the negation of his bit with probability 10%. Okay, so let's... And okay, so then they select, they have a new vertex, and then they basically move to the child indicated by this bit. Okay, so everyone, okay, let's see the example. So Alice owns the root, right? If she has 0 for the root, then she needs to send 0 with probability 90%, and she needs to send 1 with probability 10%. So in this example, she sent a 0, and they get to this red vertex. And now Bob owns this red vertex. If he has a 1 for this vertex, then they should go right with probability 90%. He should send 1 with probability 90%, and he should send 0 with probability 10%. So in this example, he sent a 0, so they go here, and so on. This defines a path. It's a very easy protocol. State your actual bit with probability 90%, negate your bit with probability 10%, and the players move to the child that was indicated. And then if eventually you reach some leaf, and what the players do is they output the sum of the bits that they have for their leaf. So if they got here, Alice tells Bob what xv is, he XOR it with yv, and this is the output. And okay, so hopefully this is the bit b that we're looking for. And the easy part is showing correctness. It's easy to show that this protocol solves the function, computes the function with high probability. And the reason is that by turn of bound, we're very likely to reach a typical leaf. The reason is that we're going 90% to the right direction. So with very high probability on this part of the path, we'll go at least 80% to the right direction. Okay, so on average, in expectation, we're going 90% to the right direction, and we only need to go at least 80%. This will happen with high probability. So with high probability, we're really solving this game. Is this clear? Why it's solving the function? Good. So the question is now, okay, so it does solve it, but why would I claim that the information is low? clearly the communication is horrible. The communication is the depth of the tree, which is double exponential in k. So we know we can get exponential in k, right? So the communication is horrible, but I'm claiming that the information is really small. Okay, so this is what I want to claim next. But maybe before, I want to tell you why we go 90% to the right direction and not 100% to the right direction. It seems that this will be the same, right? Or maybe better. They'll go exactly to the right place. And it turns out that this 90 is very important. It's not important that it's a 90. It's important that it's between 80 and 100. And it's important that it's not exactly 100. And the reason is the following. If the players always send their true bit, then this will reveal I. So it will reveal the noisy multi-layer. And the reason is that, okay, suppose that they agree to always say the right bit, then the first time that Bob disagrees with Alice, what she sends is different than what he had, then he knows that they probably reach multi-layer I. Okay, because if they didn't reach multi-layer I, they're supposed to agree on the bits. So the first time they disagree, he knows that they got to multi-layer I. And this is a problem because then the information cost will be at least the length, the representation of I, the size of I, which is log C bits, because I is a number between 1 and the depth of the tree. And this is too much. Log C is too much because we took C to be double exponential. So log C is still exponential. This is not good enough because in this case the information cost will be too high. It will be exponential in k. And somehow this 10% error going to the wrong direction with probability 10% will hide the I. And like intuitively, the reason is that now if Bob disagrees with Alice, he believes that with high probability this is just due to the 10%. She just negated her bit. That's the reason we disagree. It makes less sense for him to assume that this is because they reach multi-layer I. I mean, what's the probability that we reach multi-layer I? 1 over C? There is a probability of 10% that she just negated her bit, and that's the reason we disagree. So somehow the 10% hides I, and it keeps the information low.
So, I mean, when they actually hit the noisy multilayer I, they're going to notice that there's a constant fraction of disagreements, and that's going to suggest that it's noisy. But I guess the issue is that there's so many layers that this
exactly. Yeah, so what Andy is indicating is right. So the first time they disagree, okay, I told you Bob will believe that this is due to the 10% error, and okay. But then it's going to happen when they actually reach multi-layer I, it's going to happen like 100k times in a row. Like step after step, they'll disagree a lot. And this is maybe, this may reveal multi-layer I. But the thing is that, as you said, the tree is so deep that even this is not a cause for an alarm, right? Because with some good probability, I mean, the probability of seeing 100k times, disagreeing 100k times, is a tenth to the 100k, something like that, right? If we didn't get to multi-layer I, just by chance, 100k times, we were doing the 10% thing. This is only exponential in k. The number of layers we have is double exponential. It's something like that. So this event will happen many, many times. It will give some information about multi-layer I, but a very small amount of information, only k bits. Okay, so even disagreeing 100k times is not that weird. Good. Any more questions?
Well, the argument that you said now would only work better, so now I forget why couldn't it be 100 log k, the depth of the noisy multilayer?
The probability of guessing the typical node.
I see. Okay, thanks.
Okay, so the probability is exponentially small in whatever you write here. Other questions? Oh, okay. Good question. No. The answer is no. Okay. Okay, so let me just to give you some intuition on why you should believe that the information cost is O of k. So why would it be low? Okay, so I'm claiming that when we do our protocol, when we run our protocol, there are two types of vertices that we encounter: non-typical vertices and typical, and non-noisy vertices and noisy vertices. For non-noisy vertices, a player learns very little information about the input of the other player because he kind of already knew the input of the other player. Okay, so here, for example, Alice and Bob got the same bit. So when Alice tells Bob her bit, he's not that surprised. He doesn't learn a lot from that because he kind of already knew that. Of course, he wasn't sure that he actually knows that, but he was pretty convinced. Like, he had a 0, she said a 0, okay, it makes sense. So it doesn't reveal a lot of information, and it actually reveals very little information. So all the vertices that are not noisy, all the things in here and all the things in here, will reveal very little information. We actually reveal information on noisy vertices. On noisy vertices, the inputs were independent. When Alice tells Bob her bit, it can give him 1 bit of information. So for every noisy vertex, the other player may learn 1 bit of information. And then we're claiming that with high probability, a typical leaf is reached. This is what we said before. We're solving the game with the function with high probability. And therefore, we're very likely to only reach 100k noisy vertices. Only the vertices in multilayer I are going to be noisy. So we're paying 100k information for this, okay, because the 100k vertices times 1 bit of information for each. And I'm claiming that for all the rest of the vertices, the guys in here and all the guys that are in white, will give us very small amount of information. And therefore, you should expect that the information is O of k. And note that here, we had to be very careful with designing the bursting noise. We want to put noise over the whole thing here, but we can't. We must make this, we must allow for this path to path to only encounter white vertices with high probability. So if everything here was noisy, then this path will encounter too many noisy vertices, and then the information will go up. So we must make sure that everything in here is non-noisy. Okay, so if the path needs to go through here, this needs to be non-noisy to not incur high information cost. Okay, and so the bursting noise for the lower bound, but we need to make sure that the upper bound still works. And this is the reason we have this tapestry of noises on the bottom. So one last slide, I want to tell you what the bug is. So I said there is a little bug with the protocol. And the bug is the following. With some small probability, we do reach a non-typical leaf. So it may happen that the path will go through here. It will happen with exponentially small probability. But this is still a problem because if it happens, this is very, very deep and it's all noisy. So in this case, we may give an additional 2 to the 4 to the k bits of information, which is too much because, you know, this times this is double exponential. We can't afford this. So this is luckily easy to correct, and the way to correct it is that we have the players abort when they reach this situation. So if you reach the bursting noise, we ask the players to abort, and it turns out that they can actually detect, they can actually tell whether they got to the bursting noise. And basically, they can see that if they reach the bursting noise, then they're going to disagree exponentially number. Let me say it again. So to detect whether you got to the bursting noise, the players will try to see whether in the last exponentially many rounds, they disagreed at least 80%, more than 80%. They agreed less than 80% of the time. Okay, so they have an exponential counter, something like 2 to the k, and they check whether they disagreed in the last 2 to the k rounds with high probability. If this is the case, it's probably because they got to the bursting noise, and then they just terminate and fail. But this will only happen with like small probability, something like 2 to the minus k, and this is part of the error. So we can actually take care of this annoying case. And thank you to Andy for pointing that out, because in the original version we had something more complicated. So the abort works, thanks. Okay, so this is it, I think, yeah. You have questions?
Any questions for the speaker? Okay, I have a question. So in this, if we made the randomness that a player has to help make choices, if we made that randomness also part of their input. So we said that then, like all these random choices that I'm making, because that's part of my input.
So you're revealing then you're giving too much information. Because the thing is, we're not charging for private randomness.
Yeah.
So when we disagree, I learned something about either your input or your randomness, which you call your input now.
Yeah.
And this is typically how it goes. So usually the private randomness helps us to reduce the information. It kind of allow us to hide the actual information in kind of random information that is not part of what we charge for. Yes.
Okay. Do you think that a similar counterexample would exist if you did not allow private? If I charge for everything I learned about the other side, whether it's private randomness or.
So you're saying that there is no private randomness, and this goes to Shai's talk. I don't know if he's here. Oh yeah, he's here, because then I'd be really mad, because I came to your talk. So yeah, Shai talked about the case where there is no private randomness, and this is exactly what you're saying, that this is part of the input. And then we have very good compressions, and you couldn't get something like ours. And I think Shai mentioned it. Am I saying that correctly? Okay.
Okay. Speaker.